This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's question is, what is the area bounded by y equals 3 minus 4x on 9 and x equals to 3 and the x and y axes? Like many maths problems, the first thing we do is draw a picture. The curve y equals 3 minus 4x on 9 is a straight line because it depends only on a constant term and on x. When x equals to 0, y equals to 3, so we get this point up here. And when x is equal to 3, we get y equals 1 2/3, hence we get a point here. And then we draw a straight line between these 2 points to get y equals 3 minus 4x on 9. X equals to 3 is simply a vertical line passing through the x equals to 3 spot here. And the x-axis is this one here, and the y-axis is this one here. So we're asked to find the area inside here. We will solve this in two ways. The first method recognizes that this is a trapezium, or equivalently it's a rectangle plus a triangle, and method 2 will solve it using integral calculus. We're asked to find the area of this figure. If you prefer, you can rotate it 90 degrees to get this one, and then the formula for the area of a trapezium is a half of the sum of the two parallel sides that are of possibly of different lengths, multiplied by the perpendicular height. But in this case we have a right angle here, so the height is 3, and we get the area is 7. Equivalently, we can split the trapezium up into two parts, a rectangle and a triangle. For a more general trapezium, we'd have a rectangle and two triangles, and then the total area is just the sum of the individual areas, which we work out here, and of course get the same answer, 7. Let's look at a more interesting way of solving this. We can solve this using integral calculus, and indeed the problem is asking what is the integral from 0 to 3 of 3 minus 4x on 9 dx. I'll explain this a bit on the coming slides. Once you've learnt some integral calculus, then you know to solve it in the following way. First we take the inside and we want to find a function whose derivative is equal to this. Recall that yesterday's video spoke at length about derivatives, so you may wish to watch that one before watching this video. Based on the fact that the derivative of x to the power of n is n times x to the power of n minus 1, we guess that this is the function we want, and we check that this is the case simply by differentiating it. The derivative of 3x is just 3, and the derivative of x squared is 2x, therefore the derivative of 2x squared on 9 is 4x on 9 as required. We use this slightly funny notation here. This means that we want to evaluate this function in here between x equals to 0 and x is equal to 3, or precisely, we first evaluate this when x is equal to 3, then we evaluate it when x is equal to 0, and then we subtract the 2. And so firstly, we substitute 3 in here to get 3 times 3 minus 2 times 3 squared on 9. And then we evaluate this when x is 0, but the answer is just 0, which is why I don't have anything here. Otherwise, we would have this one minus whatever we get when we evaluate this at 0. And then this simplifies to 7, giving us the same answer as before. The remainder of this video will explain why that previous trick works. Now, when discussing integration, textbooks love to draw pictures like this. They say that to compute the area under a curve, we break the area up into a whole bunch of rectangles, and the narrower the rectangles are, the better the approximation, and we need to sum up the areas here. While correct, on its own, it doesn't really explain why we had to find a function whose derivative was the curve. So instead I'm going to present the intuition in the following way. Of course this is what books do, and it directly relates to this. The key point is we're most interested in this last rectangle here, and we don't have to worry too much about all the other rectangles, as we'll see presently. The setup is as follows. Let A of t be the area under our curve, f of x, from x equals to 0 to x is equal to t. So here's my curve y equals f of x. Here are my axes. For convenience, I'm just going to assume x is equal to 0, but it's easy to have different values here. And we define A of t to be the area under the curve from x equals to 0 to x is equal to t. And the key question to ask is, how does A of t grow? Or precisely, what does A of t plus h, where h is very small, minus A of t equal to? How does A of t grow with t? Graphically, A of t plus h minus A of t is just this shaded region in here. A of t is the area in here from x equals 0 to x is equal to t, and A of t plus h is the area from x equals to 0 all the way up to x equals t plus h. Therefore, the difference in area is just this small region in here. First, understand what's happening intuitively. If I look at this figure, then when h is small, then this region here looks very much like a trapezium. And we should be able to find the area of a trapezium by using the formula from before. To make this rigorous, then we can use differential calculus. Differential calculus allows us to work out how my function f is changing in a neighbourhood of t. Recall from last video that I can write f at t plus h is equal to f of t plus, this is my linear term here containing the derivative, plus higher order terms over here depending on higher order derivatives. For this region here then, we know that the height on the left hand side is f of t, corresponding to this point here, and we know the height on the right hand side corresponding to f of t plus h is given by a Taylor series over here in h. The only thing I do not do rigorously here is argue that when h is made sufficiently small, it's good enough to assume that this is a straight line segment if we just want to know the area up to first order terms. But roughly speaking, this is how calculus works. We know from last video about the chain rule, if we make a sequence of approximations and provided each approximation is correct to first order, we can just keep on ignoring higher order terms and still end up with the correct first order approximation at the end of the day. Because we only need to know this area here correct up to first order, it's okay to assume that this is a trapezium. In fact, we could have gotten away with assuming it was a rectangle, and that follows from the mathematics here. In detail, recall that we know that this is f of t, we know that this is f of t plus the rest of the Taylor series here. We're going to assume that this is a straight line. Therefore, the area is given by a half the height, so to speak, if we rotate this 90 degrees, and then the sum of the two side lengths here that are parallel. When we evaluate this, we find the area is f of t times h. That comes from these two terms here, divided by 2 gives us this times h. And then every other term depends on h squared or a higher power of h. So as h goes to 0, these other terms rapidly go to 0. This is the dominating term, the term we just need to worry about. So what we have shown is that this shaded region in here, it is equal to f of t times h plus higher order terms in h. So when h is very small, then this area here is essentially just f of t times h. This shows us how a of t increases when we increase t, and indeed, as we'll show on the next page, this should be related to the derivative of a of t. From the previous page, we know a of t plus h minus a of t is equal to f of t h plus higher order terms in h. Bringing this to the other side so it matches up with our video from yesterday, a of t plus h equals a of t plus f of t h plus higher order terms, and we recognise from yesterday's video that therefore the rate of change of a, the derivative of a at t, is just f of t. This is the key observation explaining how we can solve integral equations. The instantaneous rate of change of the area is given by the height of the function, and this makes intuitive sense. The higher my function is, then the faster the area should grow. To summarize, this notation here on the right-hand side means draw the curve f of x and work out the area from x equals 0 to x is equal to t, the area here. And we denote this by capital A of t. What we've shown is that the rate of change of A is equal to the height of f. We did this, remember, by drawing this picture here, showing that A of t plus h minus A of t is this shaded region in here, and we can work out what this is as a Taylor series in h, and by keeping only the first order term, we see how it grows for very small h. And we found that its rate of change is simply f of t, which makes sense. The higher my function is here, the faster the area is going to grow. Our basic strategy then for solving this integral equation is to guess a function a of t whose derivative is f of t. When we do this, there's essentially a unique answer, but up to a constant. When we differentiate a constant, we get 0. So any function a of t we can get another function satisfying this equation just by adding a constant to it. What we really want is to choose the answer such that when it's evaluated at 0, we get 0. And that's simply because for today's video, we're just integrating from 0 to t. So when t is equal to 0, then the area is 0. Returning to today's problem, we're going to evaluate this integral again, but taking smaller steps. So step 1 is to guess the functional form of our area a of t. We know that a of t has to satisfy the property that its derivative is equal to this function in here. Because we know that the derivative of x to the n is nx to the n minus 1, that quickly leads us into guessing that a of t is 3t minus 4 on 9th t squared on 2, as we check by differentiating it. But I want to point out that I could also add any constant I like on the end of a of t, and I'd still get the correct answer, because when I differentiate a constant, I get 0. This means that step 2 is that I might have to play around with this constant at the end to make sure that when I compute the area at 0, I get 0, because that's my lower limit here. This is equivalent to saying, once I've found an a of t, the particular a of t that I want is obtained by taking the a of t that I found and subtracting off a of 0, because this will make sure that when t is equal to 0, I get 0 here. Today's question explicitly asks for the area from 0 to 3, so we want a3 minus a0. And so now we just substitute using the a that we found in here to get 3 times 3 minus 4 on 9, 3 squared on 2, minus, and then a of 0, same thing, but that's just going to be 0 minus 0, and we end up with the same answer of 7. For fun, we finish by asking, if we know the circumference of a circle is 2 pi r, can we guess what the area is? Here's my circle of radius r. If I increase its radius from r to r plus h, then I've increased the area by this green amount in here. If I were to just cut the circle and unravel it, I get essentially a trapezium here. The white part here has got length 2 pi r. The blue part here has got length 2 pi r plus h, because we know the circumference of a circle of any given radius. And they're slightly different lengths, so approximately I've got a trapezium here. The increase in area is simply this green shaded region in here. And we know from before that even though these have got slightly different lengths, the error that introduces into the area here is of order h squared, and so can be ignored. Therefore, we can approximate the increase in area by just 2 pi rh, the area of the rectangle here. So we believe that the increase in area, the derivative of area, should be just 2 pi r. Remember that the derivative is just the constant in front of the h term. So the actual increase is 2 pi rh, therefore the derivative is the constant in front of the h, which is 2 pi r. This means that the area is a function whose derivative is 2 pi r. So we guess that a of r is 2 pi r squared on 2, because when we differentiate this, we indeed get 2 pi r. And note that we have got the correct constant here, because when a is 0, this formula here gives us 0. So I don't have to add or subtract any constant to get the correct answer here.